So in this problem, we're given that we have this deflector elbow from which a fluid is flowing. At the inlet, the fluid enters horizontally. This is our inlet at point 1. And as the water flows through the deflector, it changes its direction. And at the outlet, I will obtain some fluid that is coming out at a velocity that is making some angle with respect to the horizontal. In our situation, the pipe makes an angle of 30 degrees at the outlet. We're given the cross-sectional area of the elbow. We can see that it's converging as it tilts up. At the inlet, we're given that we have an area A1 equal 113 centimeters squared, whereas at the outlet, I have A2, which is equal to 7 centimeters squared. We're given the elevation difference between the centers of the outlet and the inlet. It's equal to 30 centimeters. We can see it here. We're told that the weight of the elbow and the water in it is considered to be negligible, so W is equal to 0. We're given also that we have the elbow is discharging water into the atmosphere, so the pressure here is essentially P atmosphere. So P2 is equal to P atmosphere. However, at the inlet, the water that is entering here is not at an atmospheric pressure, because this is obviously coming from some pipe system in which there might be some pump, and the pressure is essentially not going to be equal to the atmospheric pressure. It's definitely something above that. And that's why we're given here that we have some P1 gauge. We have some gauge pressure that is at our inlet. And that's what we want to find in part A. We want to find the gauge pressure at the center of the inlet of the elbow. We are given that we just want the gauge pressure. So if we are to find P1, then P1 gauge will be P1 minus P atmosphere. So we have to pay attention to that. Obviously, since we're given some elevation difference and the pressure at the outlet, and we're interested in finding the pressure at the inlet, then maybe it makes sense for us to study Bernoulli's equation, especially that we don't have any pumps and we have no head losses in our flow. So we can try to solve part A by using Bernoulli's equation. So in Bernoulli's equation, we have that P1 plus half rho V1 squared plus rho G Z1 at our inlet is equal to P2 plus half rho V2 squared plus rho G Z2 at our outlet. What we are interested in finding is P1, namely the gauge pressure of P1. Let's check the values that we have versus those that we don't have. So I do have P2, it's simply P atmosphere, so I can directly substitute that. However, I don't have the velocity at the outlet. I don't have the exact height at the outlet. However, I can link the initial height to the final height, because I know that the height difference is delta Z, which is given to me here in this question to be 30 centimeters. So I'm going to actually rearrange my equation. I will have P2 minus P atmosphere on one side, and on the other side, I will have half rho into V2 squared minus V1 squared plus rho G into Z2 minus Z1. So P2 minus P atmosphere actually gives me, sorry, this should be P1. So P1 minus P atmosphere actually just gives me P1 gauge, which is what I want. And on the other hand, on the other side of my equation, I know rho, it's the density of water. I don't have the velocities. I do know Z2 minus Z1. It's the elevation difference between the inlet and the outlet, which is given to me to be 30 centimeters. So my only unknowns are just V1 and V2, which I can actually try to find from the mass flow rate that is given to me in this equation. I am given that the water is flowing at a rate of 14 kilograms per second in the pipe. So this is m dot, and actually m dot is the same at the inlet and at the outlet. So let's recall the equation of m dot. I know that m dot, which is given to be 14 kilograms per second here, this is equal to rho times the volume flow rate, and the volume flow rate is equal to the velocity times the area. This can be the velocity and the area at the inlet or at the outlet, because in this problem I have just one inlet and one outlet and a steady flow. So basically the mass flow rate is the same at both the inlet and the outlet. So this actually just directly tells me that I can write V1 to be m dot over rho A1, which is 14 over the density of water here. I'll take it to be 998 times the area, which I know is 113 centimeters squared. So I can change that to meters. And now I can find actually the velocity at my inlet. This is 1.24 meters per second. At my outlet, I can do the same thing. I'll have m dot over rho A2, which is equal to 14 over 998 times 7 times 10 power minus 4. This gives me the velocity at the outlet, which is 20 meters per second. So now that I have the values of the velocities, I can actually directly plug them here. I have 20 squared minus 1.24 squared plus 998 times 9.8 times the elevation difference, which is 30 centimeters. So I can actually solve for P1 gauge, and the answer will be 202.2 kilopascals. So that was for part A, in which we want to find the gauge pressure at the inlet of this pipe. In part B, we actually want to find the anchoring force needed to hold the elbow in place. So because I have this kind of flow, then there is some imbalance in the forces acting on my control volume. And if there was no opposing force, then this whole pipe system will actually be moving. So there should be some supporting force over my elbow in order to keep it in place. We want to find the magnitude of this force that is needed to hold the elbow. So to do that, we're actually given some drawings for this force. the force, the anchoring force is represented here to have an x component called Frx and a z component Frz, because I have x and z axes in the plane in which my elbow is presented. Basically, since I'm given these directions, I'll just stick to them. However, it might show up that my force does not have a positive x component, for example. So if, while I'm solving, I got a negative x component, which is what I expect, to be honest, because this elbow with its flow in this direction, I expect some kind of supporting force that looks like this. I will need some support here in order to exert a force like that in order to keep the elbow from moving. However, I prefer to start with some random direction, assuming everything to be positive as is drawn in the figure here. So we just take Frx to be to the right and Frz to be upwards, and if any negative signs show up, then this means that my choice of direction has to be switched. Now to study the forces, I'm going to use the momentum equation. So this is my momentum equation, and let's look at the quantities. Again, my momentum equation is a vector equation, so I need to resolve it into components before I work on it and try to extract some quantity or some unknown. My force, as you have seen before, it has an x component of Rx and a z component of Rz. And I need to find both components in order to find the force itself. So I will actually start by projecting along x. In this problem, I have no weight forces, so I'll just remove F gravity. For the pressure forces, well, my elbow, I have chosen for my elbow the following control volume, right? This control volume feels P atmosphere everywhere, except at the inlet, where in addition to P atmosphere, I have the gauge pressure. So this is the only unbalanced pressure force that I will have. So, and it is horizontal in the positive x direction. So for sigma F pressure, everything will cancel out because I have P atmosphere everywhere, except at the inlet, where in addition to P atmosphere, I have P1 gauge. So I can just multiply this by A1, and this is the net pressure force that I have in this situation. My control volume cuts through the pipes so that I don't have any viscous forces. And I need that essentially because I want to consider the external force, Fr, that is exerted on my elbow. So I cannot take my control volume to be within the fluid inside the boundaries. It has to cut through the elbow, and thus essentially I will not have any viscous forces because the viscous forces are exerted or exist in my equation only in the situation where my control volume is within the fluid only and not cutting through the pipe holes. So here we don't have viscous forces because CV is outside the pipe holes. In F other, I will actually have my external force. It's x component only because I'm projecting along x so far. I have a steady flow, so I can remove the time dependence. And I have one outlet, one inlet, so I can directly just substitute these. My equation becomes like this. I have at the inlet and at the outlet beta and m dot. I will have V out minus V in. I am projecting along x, so both of these will be in the x direction. Now I know that at the inlet, the speed is already in the horizontal direction. This is V1 here, whereas V2 at my outlet actually makes an angle of 30 with the horizontal. So when I'm projecting along the x-axis, I have to be careful about these quantities because this will actually give me beta m dot. At the outlet, I will have V2 cosine 30. This is my x component, whereas at the inlet, I have V1 itself. I can just rearrange my equation. I will have Frx is equal to beta m dot V2 cosine 30 minus V1 minus P1 gauge times A1. I actually have all of these values. Beta is given to me in the problem. We are assuming a fully developed turbulent flow for which beta is equal to 1.03 in this problem. So I'm just going to plug that here. The mass flow rate is 14 kilograms per second. V2 is, as we found in the previous part, it's equal to 20, whereas V1 is 1.24. And we just found P1 gauge in the previous part as well. It is 202.2 kilopascal. So I'll multiply that by 10 power 3. And A1 is 113 centimeters squared. So I'll multiply that by 10 power minus 4. We will end up with the x component of our force to be equal to 2053 with a minus sign. Now the minus sign directly tells us that we have a negative x component. So actually our Frx is actually in the negative direction. Now we can do the same approach, but along the z direction in order to find the z component of our force. So I'm repeating the same thing, but along the z direction. Again, I don't have any gravity forces because I am told that I have a negligible weight. Otherwise, in this direction, I would have to account for the weight of my liquid and the pipe itself. For the pressure forces, well, in this situation, we said the only unbalanced pressure force is P1 gauge, which is at the inlet, but that is essentially horizontal, so it will not have any Z component. So this also cancels out. Again, my viscous forces are 0 because my control volume cuts through the pipe. And F other will contain none other but the Z component of the applied force, which we want to find. I have a steady flow, this goes away, and again I have one inlet, one outlet to account for. So my equation becomes like this. I have FRZ, which is equal to beta m dot into V2 in the Z direction minus V1 in the Z direction. Now let's look at the components of our velocities and what are the values of their Z components. At my inlet I have V1, which is horizontal, so it will actually have no Z component. At the outlet, I have V2, which is oblique, so it does have a Z component. Actually, its Z component will be V2 sine 30. So we will end up with the following equation. V2Z is going to be V2 sine 30, and V1Z is 0 because V1 is horizontal. So this gives me 1.03 times 14 into, we just found V2, it's 20. So we can calculate this and we'll get 144 newtons. This is positive, so actually our applied force looks like this. This is Fr that is needed to support our elbow. It has a negative Z component, a positive Z component, and a negative X component. This is Frx, which is in the negative X direction, and this is Frz, which is in the positive Z direction.